Hello, ladies and gentlemen. This is Mr. Hunter, and these are your momentum notes. I am going to try to finish them in one part, and then on the back where it says like motion notes examples, I'll give you some examples in class. So, momentum is inertia in motion or mass in motion. And remember when we were talking about the physics of car crashes, he actually introduced it in the video where he was saying, hey, definition is of momentum is inertia and motion, and we use the letter P, well, although I don't know why I wrote it like rho. So we write it as P. Don't know why they chose that. But momentum is simply your mass times velocity, and the unit is kilograms times meters per second. So momentum is your inertia in motion, it's your mass times your velocity, and the unit is kilograms times meters per second because mass is measured in kilograms and velocity is measured in meters per second. So with momentum, we also have the conservation of momentum. And just like energy, like conservation of energy, energy can't be created or destroyed, and the energy before equals the energy after, we could say the same thing about total momentum. And that's why I have an underline here. The total momentum before the collision equals the total momentum after the collision. So when two objects are colliding, the momentum is conserved. This is how officers often can figure out from like tire streaks and stuff, like the overall velocity of the car, and they can figure out the before and afterwards of the collision using actually this equation. I'm just going to zoom down a little bit so this all fits. We'll go back to 100. Ooh, maybe not 100. So the total momentum before has to equal the total momentum after, which means that the mass times velocity of the first object has to equal the mass times velocity of the second object after the collision. So this means that the combined momentum of both objects before the collision equals the combined momentum of the objects after the collision. So for example, if I was at a shooting range and I was sitting there with a rifle and shooting at a target, the momentum before I release the trigger is 0 kilograms times meters per second. Why? The bullet and the gun are both at rest. But once that pin hits the bullet and ignites the gunpowder, the bullet is going to shoot out. And then if I know the speed of the gun and I know the mass of the gun and I know the mass of the bullet, I can actually figure out how fast that's the speed of that bullet is. So let's see. I don't think I can go over specific. Actually, I could do it like that. Yeah. So impulse and change in momentum. So as we talked about in class, impulse is your force times time. And so force is measured in newtons, time is measured in seconds. So impulse is just your force times your time. So as we did in class with the eggs, when I threw the eggs at the blanket, we threw them with the same momentum, but we increased the time so that we could decrease the force. So an impulse is a force acting over a period of time. This is why your cars have airbags, because if you were to get into a car accident, the airbag deploys, which increases the time that your head will hit that dashboard so that you can decrease the force that's acting on your body. So an impulse creates a change in an object's momentum. Think about it. Before that collision, you had some mass times your velocity, and the impulse that is being presented by that airbag and the car crash is changing your momentum and reducing it to 0 so that you can eventually come to a rest. Which means that since impulse equals the change in momentum, we could say they're equal. Which, if impulse equals change in momentum, that means I could solve for the other parts of the equation. So force times time equals mass times my change in velocity. So if I give you change in velocity, if I give you the mass and I give you the time, you can find the force. So that means that you can find these other variables that you don't know by having the ones that you do know. So if I said, hey, does the impulse equal my change in momentum? I might give you impulse and you just have to say, hey, that's equal to my change in momentum. Or I can give you impulse and say, hey, find the mass, here's the velocity. or I can give you the impulse and say, here's the velocity, find the mass. It's just another equation we can use, because now that if we have 3 of these 4 variables, we can find the thing that we do not know. So in collisions, there are 2 types of collisions that you will encounter. You will encounter elastic collisions and inelastic collisions. And for this part of information, you kind of just need to know what's happening between elastic and elastic. The math actually works out the exact same using the equation that I'm about to show you. So an elastic collision, the definition is a collision in which the objects bounce off each other and do not deform or create heat. A perfect example would be billiard balls in pool. When one ball strikes the other ball, they don't bend or deform, or there's not enough friction that we lose energy to heat. So it's kind of a nice energy transfer, or in this case, a momentum transfer. So in this case, let's look at this example, and yes, you're going to be drawing this example into your notes. I just pre-wrote this out so it is easier and quicker to get through. So example billiard balls before. So we have a 1 kilogram billiard ball, and it's moving at 1 meter per second, and it's about to collide with a billiard ball that's not moving at all. So just like we did in class, M1V1 would be 1 kilogram times meters per second, because I get 1 times 1. And then it's going to hit, and it's going to be added to the momentum of the second ball, which will just be 1 times 0, which is 0. So beforehand, before this collides, I have a momentum of 1 kilogram meter per second. Then afterwards, the first billiard ball comes to a total stop, 0 meters per second, and the other one shoots off at 1 meter per second. Now, a problem I could have given you is said, hey, find the velocity that the ball flies off at. So instead of v equals 1 meter per second, you get v equals question mark. And then using this equation, you would actually solve for that 1 meter per second. So as I demonstrated in class, one thing that you should really start doing to understand momentum is you should make a T-chart. And so for your LEPA, to make it simple, make a T-chart and do before and do after. And then list out your variables. So for example, M1 before equals 1 kilogram. And its velocity before is 0 meters per, or 1 meter per second. I was looking at the wrong one. And then M2 is also 1 kilogram. And its velocity 2 equals 0 meters per second. And then after, M1's mass still didn't change, so it's 1 kilogram. And then its velocity is now 0 meters per second. And then M2 didn't change, it's still 1 kilogram. And I could have said, hey, question mark, what is it? I've already solved for it, so I could say that is question mark, solve for it by plugging it into the equation, and you would get an answer of 1 meters per second. So momentum is conserved in all collisions, whether inelastic or elastic, momentum is always conserved. Okay, so the last collision that I have to show you, and that will end these notes, is an inelastic collision. Go away. Okay, so in an inelastic collision is a collision in which the objects stick together, deform, or create heat. In this case, energy is not conserved. Energy is not conserved, which at this point is not too big of an issue for us, because next unit is what we're dealing with, energy, and this doesn't really come into play that much. So I have 2 train cars, and one train car is moving at 10 meters per second towards another train car that's moving at 0 meters per second. After they collide, they stick together. And then I said, hey, find the velocity after they stick together. Well, the equation modifies a little bit to the after, is you just add the masses together. Now, if you were to separate them and do M1 V1 plus M2 V2, and it's the same mass, it will come out to the same answer. But in this case, you do another T-chart, and you would say, hey, before it's 10 times 10 plus 10 times 0, and then equals after, it would be 10 plus 10, because they're both 10, is 20, and then I can figure out their velocity by plugging them in. So like I said earlier in class with momentum, it's kind of situation based. You have to read what's going on in the problem, and as such, with conservation of momentum, use these two types of equations, which are really the same thing. To be honest, you can use this guy exactly the same way for both types of situations, and you will still get the same answer as long as you split up your velocity accordingly, because after they collide, if they stick together, they're going to have the same velocity. So long as you keep your math right, these equations are essentially the same. If you have any questions, please make sure you record them so that you can ask them in class when this is due. Have a good one.